Hi, this is Miss Litton, and this is my wonderful Period 4 Honors Bio class. Say hi.
Hi.
And we are starting our chapter 25, which is the control of gene expression and cancer. So we'll get through gene expression today, and next time we'll get cancer. Yay. All right. So, yay. And then still log in as yourself for the clicker questions, so just be yourself. So here's the deal. This part always amazes me. Always. To think that you were just one cell. One cell. Look up here at me for a minute. One cell. And right here, this is where your father's sperm penetrated your mother's egg. Right here. Okay? And from that one cell, you became millions of cells. Okay, sorry, I was just making sure it didn't get interrupted. You became millions of cells from that one cell, billions of cells from that one cell. And when I look around this room, you are beautifully and wonderfully made in a non-creepy teacher way. And think about how well you function. All of us can have issues. Maybe you have some digestive issues. Maybe you have vision issues. Maybe you have some hormonal issues. All of us can have issues, but you function very, very well. And every single cell in your body has... Oh, yeah.
Between 11:30 and 1:45.
11:30 and what?
11:45.
Great, thank you. We appreciate that so much.
Thank you.
Bye. Okay, so those were like eye covering. I know. At first, I'm like, what kind of headband is that? I just wouldn't have worn it, you know. But I understand now. Oh, hi.
Can we cover people for you,
At the end of class.
Okay, sounds good.
Okay, thank you. Yeah, we got that all recorded. Yay. Okay, so every cell in your body has the exact same DNA in it. Every cell in your body has the exact same code book in it. So think of it like a textbook. But different cells in your body pay attention to different chapters in the book. Right? Okay? So you, for instance, you have enzymes to digest proteins. Pepsin, trypsin, chymotrypsin. These are 3 different enzymes that digest proteins. And you want to make those in your stomach, you want to make those, you know, in your pancreas and release it in your small intestines. You do not want to make those enzymes in your brain. What would those enzymes do to your brain? Digest your brain. Okay? That would be like super bad on the super bad scale. Okay? Because you don't want to turn those genes on, yet those genes are there. You could turn on the genes in the palm of your hand to make another nose. I mean, I guess that would be good if you weren't sure how something smelled. You know, you could smell it from a distance, right? But we have all the DNA to make another nose right here on the palm of your hand, but we don't turn those genes on. Some of you are still growing taller. Am I going to grow any taller? This is it for me. I can only grow wide. I cannot grow tall. Okay? Those genes are turned off. But for some of you, those genes are going, and you're going to gain, and an inch, maybe even more, just within this school year. So different genes will be turned on at different points in our life. Some genes may never be expressed. They will always stay tightly put away. So that's what today's talk is all about, is if all of our body cells have the exact same DNA, how do cells become specialized? And to have this conversation, we first need to review a little central dogma action. So I would like, please, Blue, go ahead and review central dogma.
Go Blue.
What are the what about Do you feel confident in this? This was what your quiz was just on, right? Okay, now, Slade, here's your turn. Go ahead, slated one.
You are. So this is.
I yell in your own words.
I
Yeah.
Making a copy hard. Making a copy hard to stop. Making a copy. Okay, I'm inviting you to copy. That's the one we're using. They're not the one using. So you invited every single one of our teachers and removed my editing app. Yeah, I don't care.
Okay, do you feel confident with in those two pictures? Okay, come back to me. So we're going to talk about how all of this is controlled. That central dogma, how it's controlled. And there are many different places where that control can be manifested. You are at an unusual point in your life right now where you have to ask permission to go to the bathroom. That won't ever happen again the rest of your life. Okay, in a few short years, you can decide when you go to the bathroom or if you need to go to the bathroom. I mean, what an odd thing, right? All day long when I'm teaching class, may I go to the bathroom? No, you may not. What are you going to do, right? So that process, when you want to go to the bathroom and it's during class, the primary point that determines whether you go to the bathroom or not is asking your what? Teacher. Now, ultimately, if you just said, I'm out of here, okay, I have to go to the bathroom, you could, right? You could run. Nobody's going to inhibit you from, you could race on out here. But a lot of times we don't do that. Social protocol, we would make sure we had permission first. But let's say you really had to go, and I said, sure, yeah, go to the bathroom. But you get to this door right here, and for some reason this door is locked shut from the outside, and you're like, I can't get out. So I gave you permission to go, but you couldn't get out of this room. This would be similar to DNA that needs to get out of the what? Nucleus. If there's something preventing that DNA from getting out of the nucleus, it doesn't matter if we made the mRNA that we could use to build a protein, we can't get the DNA out of the nucleus. Or let's say you get out of the room. That's not the problem, but you forgot to get pass, and so yard duty lady stops you and says, where are you, who are you coming, and you're like, I just have to go to the bathroom, I promise I have permission. She goes, no, you're going to the office. I have to go to the bathroom. Okay, and you still don't get to go. Or maybe you don't run into a yard duty lady and you get as far as the bathroom and you go to open up the bathroom door and it's locked. Maybe you're a piece of mRNA and you cannot get on the what? What do you have to get on? Ribosome. Or maybe you get into the bathroom and you need stall time and all the stalls are taken. Or maybe you get in there and you have your stall time, but there's no what? Toilet paper. Okay? These are all points of control. And they all, when we talk about transcription, that's the primary point. Oh, hello. That is the primary point of control. And RNA polymerase has to get on the what? RNA polymerase has to get on the what? RNA polymerase binds to the promoter. If you're going to start transcription, that is the first and big point of control. And that's like your teacher saying, yes, you can go to the bathroom or you need to wait just a little bit. RNA polymerase has to bind to the promoter. Okay? But in order for you to ask your teacher and then to go even leave the room, you would have to get up out of your seat and come and ask me, yes? If you are frozen to your seat, if your legs aren't working, you can't even get up to even ask the teacher. Sometimes the DNA is so tightly put away and so coiled up that even though RNA polymerase wants to bind to the promoter, the DNA is put away, it has no access to it to even ask. It'd be like, I guess, if I hid in my office and you couldn't ask me. Okay, it didn't matter. You can't even get to that next step. Okay, so that part of it, your DNA being available, that's also a point of control. Discuss with your bio buddy. Where else on here do you see points of control? Discuss with bio buddy.
Yeah, that's what I was thinking. Not being able to.
Be specific. Okay, so now tell me, where can I put one of these? Where's another point of control? Where? RNA processing. What do we do for RNA processing? Put on a keep going. Cut out the introns. That's all part of processing. What else? Before it leaves the nucleus. That's another part of control. Capping, tailing, ability to leave the nucleus. Where else do we have control? Ribosomes, yeah. For translation, can RNA polymerase can mRNA bind to the small and large ribosomal subunits? There are things called small interfering RNAs, siRNA. Now, RNA is what? Double or single-stranded? Single-stranded. So sometimes what can happen is because it's single-stranded, a little small interfering piece of RNA can bind on and be complementary to it. So that can inhibit whether or not it binds to the ribosome or the tRNAs are able to land. Where else? Where else would you see a point of control? Maybe here where there's a label. And this would be because we put on a what? Cap and a tail. It might get digested. If it gets digested out in there, then into smaller pieces. If it gets degraded, this is another point of control. Okay, and there's another place too. Anybody find one more? Okay, I'll tell you this one. Okay, and this is here to get a functional protein. Do you remember how we talked about chaperone proteins and the folding of the protein? Okay, and how that has to be. I don't know, you probably fold your laundry sometimes. Maybe your mom folds your laundry, maybe your dad folds your laundry, maybe you have a service that folds your laundry, I don't know. Does everybody fold their shirts the same way? No. Some of you are like super anal and you've got the, and then you flip down here. Some of you have a shirt folder like Sheldon Cooper does in order to fold that he got at the Gap, right? To make it perfectly even. Some of you might hang your t-shirts up. I don't know. Okay? But depending on whether you fold it, how you fold it differently. Chaperone proteins will make sure that the protein is folded in the appropriate way in order for it to be functional. We know that proteins are always very what? Specific. Exactly. Very specific. And if you fold it in the wrong way, it may not work. Yes?
So do RNA, do things only get digested horizontal? Because, there's a cap in the tail, but there's nothing covering,
the interior?
Yeah.
No, things can be digested there's for instance, in proteins, there's endo and exopeptidases. So it could come in there too. So that would have an issue with how long that mRNA lasts too. Sure. I don't know any. I'm just assuming there's something that could go in there. But you're more likely to probably get a little piece of RNA that's adhering to it in those sections. Okay? So all of these are points of control that we're going to discuss, and this is what leads to differential gene expression. So different genes are turned on and off at different times in different ways. Anywhere along there are points of control. So on your introduction right there, all cells have the same what? DNA. How do cells become specialized? Differences in gene expression. Differences in gene expression. Genes are turned on and off at different times and in different cells. Slate, tell them number 3. Now, what kind of cell do you think is more complicated? Prokaryotic cell or eukaryotic cell? Eukaryotic cell, a little bit more complicated. So we're going to start by talking about control of gene expression with a prokaryotic cell like bacteria. Now, bacteria are only going to make the enzymes they need when they need them. That makes sense, right? Think about your bedroom right now. You're here, you're not at home. Should your bedroom light be on? No. Do your parents ever get mad at you for leaving lights on? Yes. Hey, how about this? Should your shower be on right now? No. What if you turned on your shower, and then you went to school? and your parents already gone, and they come home before you, and they see your showers running all day. What do you think would happen? Bad things? Okay. You know how expensive water is here in Oak Park, right? You leave that shower running if you leave it too long warming up, right? That could be a problem. So you only turn on the genes as you need them, and that's what bacteria will do. They will adjust what proteins they make based on whether they are required at that metabolic moment. And so we're going to look at an example of that. Just give your notes a rest just for a minute so that you'll know, I'll help you fill them out, okay? I just want to make sure you grasp it. Okay, so take a look at this picture. You can see DNA in the background. Obviously, DNA is not normally colored. This is just shadowed because we don't speak DNAs, and so this is telling you what that DNA is in charge of. So this section right here, you should be familiar with. You know what a promoter is. What is a promoter?
The RNA transcripts.
Yeah, that's where RNA polymerase binds. It doesn't start transcribing until a little bit later. It'll start transcribing, but this is where it binds on to the DNA, onto the promoter. Now, right next to the promoter is something called an operator. Based on the condition of the operator, you can control whether or not RNA polymerase can bind to the promoter. And here's the situation. This yellow thing right here is called a what? It's an active repressor. The repressor can bind to the operator. And by it binding onto the operator, it makes it so RNA polymerase can't dock in correctly to the promoter because it kind of extends a little bit over here. And by doing that, it's not allowing these structural genes to be transcribed. It's in essence turning them off. Right now, is there an inhibitor preventing your shower from running right now? Yes. And if you want your shower to run, you turn the knob right on your shower. However you go about doing that, you turn it and it allows the water to flow out, right? And you can control how much hot water, cold water is flowing out depending on what knob you have open. You agree with that? Same thing here. Nobody is taking a shower, so there is an inhibitor right here. And it stays there until these genes are needed. And by the way, this is plural. This is genes. So there could be genes X, Y, and Z, all controlled by this one operator. Now, where this came from was a long time ago. When you called into a town, there was one line that went into that town. And the operator would answer, and she would say, who would you like to speak to? And if they said, I want to speak to the Joneses, then they would plug the line into the Joneses, and it would go out to the Joneses' house, and they would talk. If somebody else called in, they would plug it into that family's name. Does that make sense to you? And so that's why the operator, historically, people knew what that meant. It was a point of control. The operator determined who that person spoke to. So in this case, if there's a repressor on the operator, then that shuts off all of these genes. So they're controlled as a unit. Now, where did this repressor come from? Farther upstream. Okay, and that's why you have this little hashtag right here. There's a regulator gene. This regulator gene would need to be transcribed into mRNA and then translated on a ribosome into this active repressor that's binding here. So this gene also needs to be transcribed and translated because this is a protein. Okay, just based on that preliminary knowledge, could my youngest bio buddy, yow in this picture, go ahead. Youngest bio buddy.
So basically you have a section of your DNA that and right next to it you have a section that basically controls what is on the carbon. And there's some people right
Once you share with everyone.
really operator.
Oh yeah, an accident.
Basically
All right, oldest bio buddy, you have an opportunity. I didn't explain this picture, but your large mammalian brain ought to be able to dissect it. Okay, oldest bio buddy, this picture belongs to you. Break it down, you can do it.
Like the repressor.
Well, the regulator gene codes for the repressor.
Okay, so before
Yeah.
there was repressed DNA, there was just the gene for the repressed DNA.
Yeah. Oh, well, why don't we handle this? It's not a chicken and the egg kind of thing.
Okay.
Okay. Come back to me here. Okay, so this is showing you this regulatory gene being right next to the promoter. It's not normally, it's farther upstream. They're just simplifying it for you. So this regulator gene, if it's transcribed, it makes this mRNA. This mRNA would go get on a ribosome. You would translate it into this active repressor. Not all repressors are born active. Some are inactive, okay, and have to be activated by a co-repressor. I just want you to know that, because sometimes people go, oh, all repressors start repressing. Not all of them. Okay, so here this active repressor, it's binding onto this operator, and this RNA polymerase, who looks like a giant egg, therefore can't get on the promoter and bind well, it can't move down this line, making some mRNA, which then could be coding for some sort of protein. Is the repressor being mean? No. If the repressor is there, it's because why?
It doesn't need anymore.
It doesn't need whatever this is coding for. It's like turning on, you don't want to have your shower on if nobody's there to take a shower. You don't need it. Leave the shower off. When you need it, you'll turn the shower on. Okay, so let's write some initial notes on here. Go to introduction. A bacteria's environment is always changing. So then are the necessary proteins. An operon in bacteria, genes are often clustered into units which allow the expression of several related genes to be controlled as a unit. As a unit. Okay, the regulator gene is normally outside of the operon. It codes for a repressor. It codes for a repressor. Okay, so an operon, okay, is the promoter, the operator, and whatever structural genes you're controlling. So that regulator gene is normally outside of it. So if you look at number 1 under operon, right, see how I have it bracketed? Why did I have it in brackets? Because it's not really what? A part of it. It's outside of it. That's why it's in brackets. I just wanted you to know. Okay? And B, the promoter is where RNA polymerase initially binds. The operator is the region where an active repressor binds, preventing RNA polymerase from binding to the promoter. And then blue, you tell them letter D.
Structural genes code for the enzymes and protein that I don't want to make notes of these.
Then we'll just do these notes. Yeah. We're tight. You guys are. What are you doing?
Wait, code.
That's why I never want to make notes of you as the owner.
Okay, now, come back to me. Figure out that independently, please. Okay, come back to me. Let's think of a reason why we would want to then turn on these genes. Let's look at a scenario. Okay, so first of all, get your bearings on the DNA. What does the regulator gene do? What does the regulator gene do? What does it do? Tell me, tell me. Yeah, it codes, right? Codes for the repressor. So that's what the regulator gene does. Here's the repressor in this scenario. Okay. What about the promoter? Yeah, the RNA polymerase is where the RNA polymerase wants to bind to the promoter, and then it wants to chug on down here and make these structural genes, whatever it is that it codes for. But like you told me, RNA polymerase can't bind to the promoter if the repressor is on the what? Operator. And the reason is RNA polymerase tries to come along here, but it can't get on. So as a result, this operon is turned off. These structural genes are gone. But that's okay because we don't need them anyway. let's say these enzymes, this DNA right here codes for enzymes to digest lactose. Well, if there's no lactose around, then you don't need those enzymes. But if this bacteria is exposed to a bunch of lactose, now we want to turn these genes on. Well, here's the beauty of this. Lactose can bind to the repressor. And when lactose binds to that repressor, it can only bind to one thing at a time. So when it binds to the repressor, then the repressor leaves the operator. Well, that's good. He's gone now. Now RNA polymerase can bind to the what? Yeah, it can bind to the what? Promoter, and move on down, and then you can end up making this mRNA right here. This mRNA, if translated on a what? Ribosome, will code for enzymes that will digest lactose. Digest, 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 and even digest here. Now there's nothing pulling the repressor away. He gets back on the operator. Is that a good thing? Yeah, because we took care of all of our business. This was a catabolic process, right, to digest, lactose. And so now that my lactose is all digested, I'm ready to shut it down. I don't need that enzyme anymore. Yes?
Would it continue to produce RNA even though, because there's no repressor there until the next repressor?
Well, the thing is that RNA doesn't stay right there. It will move along and make this one strand of RNA, and then another one will need to attach and move along, and it can't do that.
Okay.
Yeah. Yes?
This is a quick question, but is there only one promoter on the strand of DNA, or is it
this is a control unit, and there's going to be a control unit like this for every group of genes. There has to be a way to turn those genes on, and this is how you do it. This, again, is bacterial cells. Now, we still have promoters for RNA polymerase, but we work a little bit differently, and I'm going to differentiate that out in just a minute. Okay? More on this. Yes?
So, when does the repressor come like automatically, or do you have to like go through the entire RNA once before you can get the repressor?
Okay, so remember, where's the repressor coming from?
The regulator.
Yeah, so this regulator gene codes for repressors.
So like,
And as long as that repressor is there, this is a type of repressor that doesn't need to be activated. It's ready to bind on right away. And as long as he is there, he will bind on to that operator.
okay.
Yeah. Okay, now let's try, and I'm going to give you another picture. You should have no problem explaining it. We will have dark-shirted BioBuddy go first with the first slide, and then light-shirted BioBuddy will finish it up. Dark-shirted, here you go. This is part one of this story. And then light-shirted will do part two. Go ahead.
He actually presses this on now, when binds with the repressor decides.
Okay, and here's part two.
we'll just kind of like
Go ahead.
part two press lactose if present binds
That's basically.
Wait, let's ask this out loud. Okay, let's talk questions. Go ahead.
So if the repressor is like not needed anymore, where does it go? Because you are going to use the regulatory gene to make a new active repressor.
That
So,
repressor
like,
can become active again as soon as the lactose is gone.
yeah. So then why do you need the to create a new one? Though?
Oh, okay. So we're not talking about the levels of control before that. We're just
Oh,
focusing on just
okay.
this one. But I think those are great questions. There's another whole set of controls that control whether that gene is transcribed. Layers on layers on layers.
Okay, so it's like a.
Yeah. Okay, so let's write some notes about this. The lac operon, do you know why they call it the lac operon? What are we trying to digest? Lactose. Good. The lac operon is what's called an inducible operon. If I say something is edible, sorry, I've been talking about Google Docs and making it editable, but let's talk about food and say edible. Have we eaten it yet? No, but is it edible? Yes, okay. So this type of operon is called inducible. We're not making whatever its product is yet, but we can do it. Who acts as the inducer to get this made? Who made sure that these genes were transcribed and translated? Who flipped the switch?
Repressor?
No, the repressor didn't flip the switch. The repressor was turning things off. What did we do to get the repressor to go away? Added lactose. Lactose was the inducer. Lactose was the inducer. It got it to happen. So, number one, the operon was off. There was an active repressor, but it could be activated. The it in this case on what we could activate is the operon. If you want to add that after the word it, the operon was off. It had an active repressor, but the operon, could be activated. Number two, when only lactose is available, then the structural genes that code for the 3 enzymes required for lactose metabolism are produced. When only lactose is available, then the structural genes that code for those enzymes are produced. Number 3, lactose binds to the repressor and inactivates it. Lactose binds to the repressor and inactivates it. Lactose acts as a what? Inducer, because its presence is required in order to express a gene, and this is typical of catabolic processes. Typical of catabolic processes. Are catabolic processes about breaking or building? Catabolic, breaking or building? Breaking. So, you only want to make the enzymes to break something down if you have something to break down. Could the youngest bio buddy explain why does this system make sense? Why is this a good adaptation? Go ahead, explain it.
It basically says if you don't have
Because you don't digest stuff.
You have to exist.
They removed my heading. Yo, Armin.
So if
Seriously.
Okay, let's see how well you've got this.
Wait, right? I thought that was the easiest. Okay, now try the sweetie.
If you see somebody's name on this list, help them. Come alongside them and say, let me assist you. I want to help you with your learning. I am your friend. Natalie has a clicker. For her? Are you putting her ID number? Maybe you don't have the ID number right. It is in. She's in. Ah. Okay, let's talk about it. Did you elicit it? Name the part of the operon system where the repressor binds. It binds to the operator. No? What? RNA polymerase is the one that binds to the promoter. Is that what some people put? Put the wrong. There we go. Yes, one person put that, and then C, regulator. Okay, so the repressor doesn't bind to the regulator. What does it do? Yeah, the regulator gene codes for the repressor. Okay, but the repressor binds to the operator. Check your BioBuddies clicker. Do they get a gong or do they get a little shame bell?
What do you mean?
No false shaming. No false shaming.
No, because he logged in as mine.
Okay, don't do that.
No, like, how do you have his ID?
And then I got it right on his.
Yeah, and he got it right on mine. And I got it wrong on his.
Good job, guys.
Okay,
I'm not reading this.
let's not celebrate ignorance.
I like read this 4 times and oh yeah. I think that was never read a book. So I method goes in into like sometimes for school books that's what I well, I don't really care if I don't care because I'm not worried about it reading it by myself. Actually, that is true. Yeah, because like you have no choice to read it, so you're sort of like, I'm looking forward to it. You don't like it.
Okay, so who codes for the repressor? Regulator gene, not the promoter. What happens on the promoter?
The RNA polymerase.
RNA polymerase binds the promoter. And 7 of you said structural genes. The structural genes code for whatever you're getting controlled for. In this case, it was lactose digesting enzymes. And then not lactose. Lactose binds to the what? Who does lactose bind to? To repressor to pull them away. Check your BioBuddies clicker right now. If they miss this, they need help. Come alongside. Ring the shame bell, but make sure they're getting it.
So, Carl's got like 5 minutes.
Good job, David. Good job, Joyce.
Done this so long.
Jackson.
Yay. I bet it's black.
I'm so tired. I think the lactose thing is
Lactose
just
codes
named
its
after
own
the
digesting
flag.
enzymes. No. I'm so funny.
Huh?
No.
Oh. Okay, if you see a name up here, come alongside them, help them.
If I got it right, I mean, if I got it wrong,
I don't like the doctor. Frankenstein is
Okay, so most of you got that. Check your BioBuddy right now. If they missed it, could you help them a little bit? Because most of you got that. Take a look.
They can hear my
Little tip, we're working our way through the list, so.
Wait, why do I? This is like.
I'm sorry, I was reading that wrong.
It makes the press
You see a name on this list, come alongside them, help them out.
You have to reread it. I read this after.
All right, so let's talk about this before I hit stop. When you see the word operator, what key things come to mind when you see the word operator? Operator.
It's where the
Who binds to the operator? Yeah, so the repressor can bind here. Okay, when you see the word promoter, what should come to mind?
RNA polymerase.
Yes, this is where RNA polymerase binds. Okay, when you see the word regulator, what comes to mind?
Codes for that makes
Codes for repressor. Good. When you see structural genes, this would be your, they code for whatever product you're controlling with this operon. What about lactose in this example? What was it? It's an inducer. It would bind to repressor. Yeah, let's see how you did here.
That's not a honey.
Okay, so we'll keep talking through this a few more times. What will bind to the repressor, making it inactive? Okay, now it's something that's hooking on to the repressor. The repressor will bind to the what? Operator, okay? But it's saying what will bind to the repressor, making it inactive. The it in this case is the repressor inactive. So that's why you would want to have picked lactose. Some of you said the promoter. The promoter does not bind to the repressor ever, okay? C, the regulator. No, the regulator codes for the repressor. So check with your bio buddy right now and see where is it that there's a disconnect. Okay, discuss right now. Did you get it right, or are you struggling a little bit?
The Frankenstein one is but I just don't understand the Frankenstein.
All right, last chance to get a hundy.
You're not supposed to read the water and creature. You didn't read it? They met and then on stage and everything.
Yay, thanks, nice. Just back, maybe 3 there and 3 on that side. That would be awesome. Okay, wait, maybe over here. Yeah, 3 there, 3 there. Thanks, guys, so much. We super appreciate it. You don't get it right, you don't get your pizza. You're hurting, you know. Okay, they wouldn't have done that on purpose. Now let's talk through this. RNA polymerase binds to the promoter. RNA polymerase binds to the promoter. Okay, so we should not still be missing this at all. Okay, let me pause our video here for a moment. Actually, I'm going to go ahead and stop this. We just discussed prokaryotic control of gene expression. So we'll pick up in another video for eukaryotic. Hope you're having a good day, good evening. If it's late, have a piece of